Hello everyone, myself Gaurav Mukwana, Assistant Professor of EC Department at LJ Institute of Engineering and Technology. In last session we have studied unit number 1, that is Introduction to Satellite Communication. In this session we will start unit number 2, that is Orbits and Launching Method. In this session, we will cover Keplers Law and the introduction. Before starting a Keplers Law, we must know the law governed by the satellite. Actually, a satellite orbiting the Earth follows the same law that governs the motion of planets around the Sun. So, the laws for satellite, which was given by Johannes Kepler, which are known as Keplers First Law, Second Law, and Third Law. These three laws describing a planetary motion. It can be applied to any two bodies. Two bodies are primary body and the secondary body. Primary body stands for the Earth. That means our satellite is rotating around the Earth. So Earth is primary body and satellite is secondary body. We will start three laws given by a Keplers one by one. First, we will start a Keplers First Law. The Kepler's First Law states that the path followed by satellite around the primary will be an ellipse. That means the orbit of satellite is in the form of ellipse. Over here in this diagram you can see this is a center of ellipse. F1 and F2 are two focus points which are also known as foci. The distance from the center of the ellipse to any of the focus point is called semi-major axis. The whole distance is called the major axis. Okay, and the line which is perpendicular to the major axis is known as a minor axis. So this whole line is called minor axis. Then half of the line is called semi-minor axis. It is represented by a small b. So eccentricity, which defines the shape of the orbit, is represented in terms of semi-major axis and semi-minor axis, which is represented in terms of equation, that is E is equal to under root of a square minus b square upon a. Over here, the eccentricity and the semi-major axis are the two most important orbital parameters which are specified for satellite, which is orbiting around the Earth. If you want to define the eccentricity for elliptical orbit, then its value lies in between 0 to 1. And for circular orbit, its value is 0. So this is the Kepler's first law. Now, the Kepler's second law. It states that for equal time interval, a satellite will sweep out equal area in its orbital plane. How? I will explain you with the help of one diagram. Over here, this is our Earth, and this is the orbit on which a satellite is rotating around the Earth. If you assume that satellite will travel a distance from this point to this point, that is S1 meter in 1 second, and also after some time a satellite will cover this distance from this point to this point, that is S2 meter in 1 second. So for equal time interval, for over here 1 second and 1 second, a satellite will sweep out equal area, that is A1 is equal to A2, because of equal area law. So it follows that velocity at S2 is less than velocity at S1, because this point is farthest from the Earth and this point is nearer to the Earth. And how a velocity at S2 is less than S1? I'm going to explain with one diagram. Over here you can see that this is Earth and this is the orbit on which a satellite is rotating. You can see that these points are nearer to the Earth and this point are farthest from the Earth onto this orbit. So gravitational force of Earth onto this point is higher than the gravitational force at this point. So the velocity will going to increase as this point is nearer to the Earth, and velocity will going to decrease because it is farthest from the Earth. So impact of gravitational force will be less at farthest point. So based on the Kepler's second law, these blue areas are equal. Because of equal time interval, a satellite will sweep out equal area. So the speed of satellite is faster at this point and it's going to be reduced as it moves away from the surface of the Earth, right? So this is a Kepler's second law. Now Kepler's third law. Kepler's third law states that the square of periodic time of orbit is proportional to the cube of a mean distance between two bodies. Over here, a mean distance is equal to or it is same as a semi-major axis, that is small a. So if we want to write the Kepler's third law in terms of equation, then it can be represented as A cube is equal to mu upon eta square. Over here, the square of periodic time. This is the periodic time. So the square of periodic time of orbit is proportional to the cube of mean distance. Mean distance is represented as semi-major axis. So proportionality will be represented as with the help of mu. That mu is the Earth's geocentric gravitational constant. Its value is represented as 3.986 into 10 raised to 14 meter cube per second square. Okay. Now, the Kepler's third law, it also gives the orbital period. In second, which is represented as a capital P. So P is equal to 2 pi upon N. If we want to calculate the radius of circular orbit, for which a period is 1. So over here period is given in terms of day and the unit of period is a second. So we have to convert the day into second. So we know that 1 day is equal to 24 hours. 1 hour has a 60 minutes and 1 minute has a 60 seconds. So 24 multiplied by 60 multiplied by 60, that is 86,400 seconds. So this is the value of period. So if we want to calculate the value of N, so it is calculated with the help of this equation. N is equal to 2 pi upon P. The value of P is 86,400. So we will get N is equal to 7.272 into 10 raised to minus 5 radian per second. Now, summary of Kepler's three laws. First law defines the orbits of planets are ellipse with Sun at 1 foci. Second law states planets sweep out equal area in equal time. And the third law defines a relationship between the size of orbit and its period. That is, P is directly proportional to a raised to 3 by 2. Okay, these are the references. Thank you.